an experimental design. Very important topic, and we did add a lot of features to version 16 of Statgraphics and the DOE wizard in order to deal with these types of experimental designs. So I definitely wanted to spend a day, an hour, whatever, going through the ideas of robust parameter design. As far as the webinar series here for the spring, I'm going to try to schedule one more webinar in July covering analysis of variance techniques and what Statgraphics does to support the analysis of variance. We'll try to cover some of the standard things, standard designs, but also look at some more advanced designs, things like split plots that are a little bit more difficult perhaps to analyze. That'll come up in July, then I'll probably take a break in August and start up a fall series in September. The topic today, though, is robust parameter design. Now, robust parameter designs are a special type of experimental designs in which, in addition to trying to hit target values for your response variables, you're also concerned about finding conditions under which the variability in that response is small. There are often certain variables, certain factors that during production, during operation, one cannot fully control. For example, temperature may be an important factor, but it may be impossible to control it exactly. So although, in addition to finding a good temperature, a temperature that gives you the target values for the responses you're interested in, the idea of robust parameter design is that you'd also like to find a temperature at which these uncontrollable fluctuations don't have a big impact on the response. Now, a lot of this goes back to Taguchi back into the 1980s. At least he's one of the folks that made this all quite popular. And we are going to be looking both at Taguchi's approach and also at a response surface approach for doing robust parameter design. Now, robust parameter designs are experimental designs that contain two types of factors. First off, there are the standard controllable factors, which are factors that an experimenter can manipulate both while he or she's doing the experiment, but also later on during production. These are the normal sorts of factors that one experiments with, and the idea of many experiments is to find a good or optimal setting of these controllable factors so that you achieve whatever response variables you're interested in. In robust parameter design, however, there are also a second type of factor, factors called noise factors that are normally not controllable. You know, things like the relative humidity, certain fluctuations in, for example, line speeds that may not be completely controllable. And the whole idea, the goal, as you can see stated on this slide, is to find robust operating conditions. These are levels of the controllable factors that give you the desired value for the responses, but also make those response variables relatively insensitive to variation in the noise factors. Now, as I had indicated before, these are the types of designs that Taguchi popularized back in the 1980s. And that whole idea of finding robust operating conditions, although it was not invented by Taguchi, he certainly brought home the fact that that's an important thing to worry about. Now, in Statgraphics, we provide two basic approaches to doing robust parameter design. The first uses Taguchi's crossed arrays. Now, the way Taguchi suggested that you do it is to set up basically two experiments. one experiment for the controllable factors, the things that you normally can set by turning dials and that sort of thing. And then a second experiment for the noise factors. Now, Taguchi called his designs inner arrays and outer arrays. The inner array was a standard design for the controllable factors. And he often used, as in classical experimental design, two-level designs where you might pick a low and a high level of each of the controllable factors and do various combinations. The additional thing that he added, though, was that at each location of the inner array, you do another experiment involving the noise factors. So, for example, you might set low temperature, low flow rate, low concentration. Those might be the controllable factors. And at that particular setting, do several experiments in which you change the values of the noise factors. Now, the noise factors do have to be controllable during the experiment, although normally in production they would fluctuate in a random sort of fashion. And the first example I will show you follows Taguchi. The second example, the second approach to doing robust parameter design, is what Doug Montgomery calls the response surface method. He also calls it a combined array, though, because what you do is you construct a single experimental design. That single experimental design will manipulate both the controllable and the noise factors at the same time. And you can use the interactions between the controllable factors and the noise factors to estimate what would be good, robust operating conditions, to estimate where the standard error of the response would be small and where it would be large. So we'll talk and see a second example using that response surface combined array approach. Okay. Now, the first example, actually both of the examples I'm going to talk about today, come out of a really, really good book by Myers, Montgomery, and Anderson Cook. I have the reference to that on the last slide. Basically, it deals with response surface methods. It's called something like product and process optimization using designed experiments. The first example from their book will be one that uses Taguchi's crossed arrays. And the example has to do with minimizing the rate of soldering defects. There's a soldering process that's to be experimented with. The basic response variable, Y, is the number of defects per million joints. Now, obviously, this is a response that we'd like to minimize. Obviously, 0 defects would be terrific, but in general, we'd like to get that as small as possible. We'd also like to find, however, a set of operating conditions that not only gave a small mean defect, but also where the variability in the defects was small, didn't vary much, for example, from day to day. Now, in this experimental design, this example, there are 5 controllable factors. There are 5 factors that can normally be controlled during production. The first is the solder temperature. The second is the conveyor speed. The third, the flux density. The fourth, the preheat temperature. The fifth factor, the wave height. We're going to call these the X factors. These are the factors that we can control both during the experiment and in day-to-day production. There are also, though, 3 noise factors, 3 factors that during production can't be controlled. The first is called here Z1. It's a variation in temperature. Now, temperature is one of the control factors, so we can, for example, go out and try to operate the process at 280 degrees. But you can imagine in practice that it may be impossible to hit exactly 280 every day. During the experiment, then, we might want to introduce a certain amount of variability. For example, run some experiments at 275, others at 285. And we would like to find a set of controllable factors at temperature, for example, at which variation didn't have a big impact on the response. Now, the noise factors here are going to be called the Z factors, and there will be 3 in this particular example. Variation in temperature will be 1. Variation in conveyor speed will be a 2nd. And the type of assembly that we're soldering will be our 3rd noise factors. These noise factors will be factors that tend to change on a day-to-day basis, normally uncontrollable. Now, we'll have to be able to control them during the experiment. But the overall goal will be to find settings of the X's so that variations in the Z don't have a big impact on the response. Okay. Now, at this point, I'd actually like to get over to Statgraphics and start setting up such an experiment. So let me flip over to the Statgraphics window, and here you see Statgraphics Centurion. This is version 16, and we're going to be starting here with an empty data sheet because what we'll be doing is initially setting up the experiment. Now, to set up a robust parameter design in Statgraphics, the easiest thing to do is to go to the DOE menu and to choose the Experimental Design Wizard. This will open up a window, and if you saw my previous seminar on experimental design, you saw this basic approach. It opens up in a new window with 12 steps. The first step, step 1, is the step at which you define the response. Now, in this example, I'm going to first type in a comment. This is going to be a robust parameter soldering study. I'll just put down a comment here that will appear on all of the output. There's a single response variable, and that's defects. Defects per million joints. All right, so I'm putting in the name of the response variable that I'm going to be measuring. Now, there's a field that specifies what you want to analyze. In most of the experiments I talked about in the last webinar, the interest was in analyzing the mean. And we still might be interested in doing that, finding a set of factors, a set of controllable factors that minimizes the mean defects. On the other hand, I might also be interested in minimizing the standard deviation of the number of defects. And one possible approach here actually would be to set up 2 response variables. One based on the mean, a second response based on the standard deviation, and try to find a set of X's that minimizes both the mean defects and also their standard deviation. However, we're not going to do it that way. We're going to follow Taguchi's suggestions. Now, Taguchi developed several of what he called signal-to-noise ratios. Most of his signal-to-noise ratios actually involve both the mean and the standard deviation simultaneously. And he had several. He had one that was minus 10 times the log of the standard deviation squared. He had a second designed for situations where you wanted to hit a target value, one when you wanted to maximize the response, the larger the better, one when you wanted to minimize the response. Now, for situations such as defects, the signal-to-noise ratio you're going to be interested in is what Taguchi calls smaller the better. So in order to follow Taguchi's standard approach, I'm going to ask it to analyze his signal-to-noise ratio for that situation. Now, the way Taguchi set up all of his signal-to-noise ratios, they were defined to be maximized. So where I have goal here, you might think I would like to minimize the number of defects, which I do. but with respect to the signal-to-noise ratio, and I'll show you how it's defined in a few moments, the goal will be to maximize that signal-to-noise ratio. So if you're following Taguchi, regardless of what signal-to-noise ratio you might pick, the goal is always going to be to maximize that signal-to-noise ratio. Now, the rest of the fields are not relevant. They would only be relevant if I had more than one response. So I'll just go ahead and set this up with one response, defects per million joints, the goal being to maximize the signal-to-noise ratio, smaller the better, Taguchi's ratio. Okay, so that's the response variable. It's defects per million joints. Step 2 is where I would go to specify the experimental factors. Now, in Statgraphics, there are 3 types of experimental factors. There are controllable process factors, process variables being things like temperatures and flow rates and that sort of thing. There are controllable mixture components. These would be components in some sort of a blending problem. And then there are noise factors that you can specify. Well, in this example, there are 5 controllable process factors, and there are 3 noise factors. So I'll set it to 5 and 3, and you can see Statgraphics will open up now 8 fields for me to specify the factors. And let's just take a few moments and put in the factors. The first controllable factor to be analyzed and optimized is the temperature in degrees Fahrenheit. For factors such as temperature, I need to give it a range, so I'll give it a range in this case of, let's say, 480 to 510. Again, I'm just repeating the example in Myers, Montgomery, and Anderson-Cook, and I hope you'll get a hold of that if you're really interested in doing these types of experiments, because it does an excellent discussion of these types of designs. The second experimental factor will be speed. The range of the experimental factor of speed will be 7.2 to 10.0. The third controllable factor was flux density, and this will range from 0.9 to 1.0. Fourth factor, preheat temperature. That's also in degrees Fahrenheit. Runs from 150 to 200 degrees. Fifth factor, wave height. And the wave height specified in inches, and in their example runs from 0.5 to 0.6 inches. Now, those are the 3 factors that I wish to optimize. Those are the 3 controllable factors. 5 controllable factors. The noise factors, the first noise factor will be the deviation in temperature. So I'll call it temperature deviation. It's also in degrees Fahrenheit. And for levels of the noise factors, we're going to specify -5 and 5. This basically says that at any time we do the experiment, we'll take whatever temperature we're interested in, like 480, and vary it by plus or minus 5. Now, often when you set up a noise factor like this, you specify approximately plus and minus 1 standard deviation. So 1 standard deviation in this case might be 5 degrees. And as you'll see when we set up an experiment, if we set up an experiment at 480, we'll actually run some experiments at 475, others at 485. We'll add that temperature deviation to the temperature. The second noise factor is speed deviation. You can imagine that it may be impossible to keep the speed of the conveyor belt exactly constant during production. And the setting for those was minus 0.2 to plus 0.2 feet per minute. And then finally, there's the assembly. And there's two types, type 1 and type 2. So now I've specified 5 controllable factors, 3 noise factors, and put in a range over which each of these will be varied. So let's go ahead, take these, and press OK. Now you can see that it's set up in my design summary, a summary of the variables that I've specified. Okay, now we've got the response specified and the experimental factors specified. The third step will be to select the design. Now, when I push the button for selecting a design, an additional dialog box will come up. And what's of particular interest first is up in the upper right corner. You will see a choice of combined array or crossed array if you're doing robust parameter design. Now we're going to do an example of both. We're starting with the crossed array example, where we'll actually set up one design for the controllable factors and a second design for the noise factors. Now if you do that, you'll see that 2 options buttons open up on the dialog box over here on the left. One for the controllable factors, one for the noise factors. I need to go through each of these to specify the inner design for the controllable factors and the outer design for the noise factors. So let's start by pushing the options button for the controllable factors. Now, I have a choice of various types of designs to specify for the control factors. I can set up a screening design. That would typically be a factorial or a fractional factorial. I could set up a response surface design, a multi-level factorial, or an orthogonal array. Now, we're going to be following Taguchi, so I'm going to select orthogonal array. But the basic principle, actually, of setting up 2 designs, one for the controllable process factors, one for the noise factors, doesn't require that you necessarily use one of Taguchi's designs. You could take a more classic design. The basic idea will be that we'll set up one design for the controllable factors, and at each experiment in that first design, do a second design for the noise factors. But since we're following Taguchi, we'll just go ahead and select his designs, the orthogonal arrays. Now, if you ask for an orthogonal array, it will bring up a dialog box showing the different designs that Taguchi proposes to use. Taguchi had a special notation for his designs. He called his designs L4s, L8s, L9s, L12s, and so forth, where the number after the L is the number of runs in the design. So for example, the one we're going to do is the default L8. That is a design with 8 runs. You'll see the notation after the L8, 2-7. That indicates that you can do 2 levels of up to 7 factors. Okay, now we have 5 factors, 5 controllable factors. So we can go ahead and use that particular design, and it will do experiments at 2 levels of the different factors. Now you'll see there are other designs like an L18 design where you might have 2 levels of 1 factor and 3 levels of up to 7 factors. Okay, it'd be a larger design. It would be a design involving 18 runs. Now, by the way, if I go back to my PowerPoint presentation, I did make a copy on the slide here of what Taguchi's L8 design looks like. In the bottom left here, you can see the 8 runs the way Taguchi lays them out. And rather than using, for example, -1s and +1s that you might be used to seeing in factorial designs, for the 2 levels of the factors, Taguchi just called them level 1 and level 2. And the idea is that you would take up to 7 factors and assign each factor to one of the columns in this design. And the run of the number 1 or 2 would tell you whether to run it at its low level or at its high level. Okay, now, since we could experiment with up to 7 factors and only have 5, the next thing we have to do if we pick an L8 design is to decide what factor goes on what column. And you will see the next dialog box in just a moment when I go back to Statgraphics will ask me what column of that L8 design do you want to use for factor A, what column for factor B, for C, for D, for E. And if I go back to Statgraphics, actually pick the L8 design, it will suggest by default that you use column 1 for factor A, column 2 for factor B, column 4 for factor C, column 7 for factor D, and column 6 for factor E. Now, the only thing this really affects is what different interactions you may be able to estimate. Taguchi has a rather involved method for figuring out if you assign different factors to different columns, then you can estimate certain interactions. Although most of the time, Taguchi actually ignores all interactions, as we will do actually when we do this analysis. Statgraphics, though, has set things up, the default assignments here, so that if you just take the defaults, if there are extra columns, and we have 2 extra columns here because we could have studied up to 7 factors, the extra columns are used to estimate the interactions between the first couple factors. So, for example, if I take the default here, one of the extra columns could be used to estimate the A-B interaction. The easiest way to handle this is if you have a particular interaction that you're interested in, make those 2 factors, A and B, take the default assignment here, and you'll be able to estimate the A-B interaction. So let's go ahead and press OK, and what it'll do when I press OK, it'll actually set up in this dialog box now the 8 runs in the L8 design, and it was done in a random order. You can see for each of the first 5 columns here, temperature, speed, flux density, preheat temperature, wave height, and so forth, that each factor is run either at the low level or the high level. Now, there are additional columns out here for the noise factors which aren't yet filled in. So in order to fill them in, I'll need to push the options button alongside noise factors. Okay. Now, this will take me through that same process of selecting a design. Again, following Taguchi, I'll take an orthogonal array. An L4 design, a 4-run design, would be sufficient to study 2 levels of up to 3 factors, and that will work. So I'll just take that, take all the default assignments, and what it will now do is it will put into the design window here a total of 32 runs. It's an L8 with an L4, an L8 inner array, and at each of the 8 runs in the L8, it then does a 4-run experiment involving the noise factors. So you can see out here in the final 3 columns now an experiment that was done on the noise factors. In fact, the first 4 runs are identical here on the controllable factors. They're all 1 point in the inner array, but the outer array involves all 4 of the factors. When I'm happy, I simply press OK. And what it will do is put this particular design into the data sheet, a total of 32 runs. And now I have a place to enter the observed defects per million. Now, one point here, when we set up this Taguchi array, we will analyze a signal-to-noise ratio. However, the number to be put in the column is simply the defects per million. And based upon the defects per million, Statgraphics will automatically estimate Taguchi's signal-to-noise ratios. Okay, so that's a typical Taguchi design. Now, rather than typing everything in, however, let me clear this all out and open up a file where I've saved the number of defects. If I go ahead and open up a data file, I actually have a data file, it's called solder2, I believe, that has the experiment and the observed, there it is, defects per million. So for example, in the first run, we had 186 defects per million. Okay. Time to analyze the data. When we're getting ready to analyze the data, we need to press step 8, Analyze Data. Now back to my PowerPoint slide for a moment. I did promise to tell you a little bit about Taguchi's signal-to-noise ratio. When I set up this design, I specified that what I wanted to estimate was a signal-to-noise ratio, smaller the better. A signal-to-noise ratio for a case where you want to minimize the response. Now, Taguchi proposed if you do that, using as your response variable, minus 10 times the log of the sum of the yi squared over n, where n is the number of observations in the outer array. Basically, what you do is at each point in your inner array, that's the controllable factor design, you take all the runs that were done, and in this case we had 4 runs in the outer array at each of the 8 points in the inner array, and you calculate this particular number. Well, I've rewritten the critical part of that number, the sum of the yi squareds over n, so you can see that that signal-to-noise ratio actually involves both the mean, the average of the runs at a particular point in the inner array, and also the standard deviation. And that's what Taguchi did. He came up with these signal-to-noise ratios that put both the mean and the standard deviation into one number, one response that we can then go ahead and optimize. Now, as far as this particular term, the one involving the yi squared over n, obviously we'd like to make that as small as possible. However, Taguchi wanted always to maximize his signal-to-noise ratios. So you can see a negative 10 times the log of that out front. The reason for the negative sign is because you then want to go ahead and maximize the signal-to-noise ratio. Maximizing the signal-to-noise ratio would minimize the number of defects. Okay, so anyway, back to Statgraphics. When I push the step 8 button to analyze the data, up will come a dialog box. I'll need to do nothing other than push OK in order to analyze the results. And here you can see that it did an analysis, fit a statistical model involving only the controllable factors. The only role of the noise factors in this particular experiment is to give me repeated measurements so I can estimate that standard deviation. With respect to the mathematical model that is operating, it's only the controllable factors that I will be able to set later on during production. And if you look at the standardized Pareto chart over here, you'll see that certainly flux density, temperature, and wave height are quite significant factors. Preheat temperature, well, it is statistically significant. It's to the right-hand side of the line. Speed, on the other hand, is to the left of the line. Okay? So we are definitely picking up some significant factors. Taguchi also liked to look at this particular plot. Okay, this particular plot is what we call the main effects plot. It shows as you change, for example, temperature from its low level to its high level, what happens to the signal-to-noise ratio. Now watch out, what we are plotting here is not number of defects, it's the signal-to-noise ratio. And you do better with big values of the signal-to-noise ratio. So what you want to do in this particular case is you want to run at high temperature, low speed, low flux density, high preheat temperature, and low wave height. And in fact, you can see the most influential factor here is flux density. So in terms of the analysis, in terms of the mathematical model, the analysis of variance, the plots, and so forth, it's all being done with respect to the signal-to-noise ratio. And the goal is always to maximize the signal-to-noise ratio. Okay, so we have a mathematical model. It gives us quite good results. Definitely some statistically significant results. At that point, I can go back to the experimental design wizard, push the Optimize Responses button, that's the Step 9 button, and I usually like to start my optimization from every point, multiple points, because it is a search procedure to make sure I get to the optimum result. And in fact, if I then scroll down, it will identify for me the factor settings. It will give me the optimal value of the signal-to-noise ratio. It says run at 510 degrees, 7.2 feet per minute, flux density of 0.9, preheat temperature of 200, and a wave height of 0.5. If I run at those particular settings, it will maximize the signal-to-noise ratio, and it's predicted, in fact, that the signal-to-noise ratio is minus 39.7. Now, there have been a number of criticisms of the signal-to-noise ratio by a number of statisticians. One thing is, it doesn't tell you a heck of a lot. I can tell you that you get the best value of the signal-to-noise ratio at those combinations of the factors, and I end up with minus 39.7. That minus 39.7, as we saw before, though, is a combination of the mean and the standard deviation. And one of the criticisms you'll see in Montgomery's book is this coupling of the mean and the standard deviation. Although it makes the optimization quite easy, you just optimize a single thing, doesn't really tell you much about what factors affect the mean and what factor affect the standard deviation. Which is why I want to show you a second approach, and that is the the combined approach. The second example we're going to look at today is also, as I said, out of Myers, Montgomery, and Anderson-Cook. This example has to do with optimizing the quality of colored television images. The response is reception quality in decibels. Now, like the first example, there are both controllable factors and noise factors. The example that I selected from their text has only two controllable factors, filter tabs and sampling frequency. The noise factors are the number of image bits and the voltage. So the basic goal of this experiment will be to find levels of filter tabs and sampling frequency which maximize reception quality, maximize mean reception quality, while minimizing the effect of image bits and voltage on that reception quality. So again, you can imagine that there are two things we're concerned about. First off, getting good reception quality on average. But secondly, finding a set of X's such that the normally uncontrollable variations in the Z's doesn't have a big impact on that quality. Now, let's go back to Statgraphics and set up this particular example. And to do that, I will clear the data sheet, clear out everything I was working with, and go back to the DOE wizard. Now, we're going to have to go through this step-by-step process again. The comment to be placed here, this is a color television signal study. Response of interest is reception quality. Okay, and it is measured in decibels. Now, this is eventually, this combined approach involves using standard screening and response surface designs. So in terms of what you analyze, it's the normal sort of, okay, build me a model for the mean. And maximize, if you would, mean reception quality. Now, at the same time, you'll see that Statgraphics will attempt to minimize the standard error of reception quality. But in terms of setting up the initial dialog box, you treat it as you typically would. You tell it what the response variable is, what you want to analyze, and whether you want to minimize or maximize or hit a particular target on that value. So in this case, I want to maximize mean reception quality. Okay. Step 2, define the experimental factors. Now, in this case, there will be 2 process variables, 2 process factors, and 2 noise factors. So I'll set it up just the way I did in the first example. The first factor is filter tabs, and they decided to run at 5 and 21. Second factor is sampling frequency, and the 2 levels of sampling frequency were 6.25 and 13.5. Again, these are typical settings that would bound the natural reasonable values, I suspect, for those controllable factors. As far as the noise factors are concerned, the first is image bits, which we'll let run from 256 to 512. And secondly, voltage, which we'll let run from 100 to 200. All right, so we've got our 4 factors, our 2 process factors and 2 noise factors specified. So we can then just press OK. Step 3, select the design. Now, as I said, in this particular example, rather than using Taguchi's crossed arrays, where you set up an inner array and then an outer array, we're going to combine all the factors, both the process factors and the noise factors, into a single design. So I'll keep the robust parameter design setting at combined array. If I push the options button next to the process factors, it says 4 process factors, but we just have to know that it's all 4 of our factors, both our process factors and our noise factors. I have a choice. I can pick a screening design, a response surface design, a multi-level factorial, and an orthogonal array. Any one would work fine. Following the example, though, in the textbook from which we got this problem, they decided to do a multi-level factorial. Now, if you tell it that you want to run a multi-level factorial, it will ask you for the number of levels of each of the factors. So, for example, I could tell it, let's run it 3 levels of filter tabs, 3 levels of sampling frequency, and 2 levels of the other factors. That will give me 3 times 3 times 2 times 2, 36 total runs involving both the controllable process factors and the noise factors simultaneously. If I do that and press OK, you'll see that it will set up a 36 run design on all 4 factors. Okay, so we have a single standard, in this case, multi-level factorial design to study those 4 factors. So let's just press OK. It will load it in the data sheet and give me a column in which to type the reception quality in decibels. Okay, fairly standard up to that point. Now, as before, I don't want to bother typing in the results. I've already saved this away. And one of the sample data files you'll actually be able to download after this webinar is over is called TV signal. So if I go and ask to open up a data file, there is a data file called TV signal. There it is, tvsignal.sgx, which has the same design, but this time it also has a measurement of the reception quality in decibels. Okay. All right. At this point, I've got my data. I can choose step 8, analyze the data. I could make a transformation, a log or something like that if I needed to. In this case, no transformation appears to be necessary, so I'll just go ahead and press OK. What it has done now, it has fit a statistical model. And if we go ahead and we look at, for example, the standardized Pareto chart, we will see that in the statistical model there are main effects. There are the main effects of image bits, of filter tabs, of sampling frequency, of voltage. There are interactions between various factors, for example, a BC interaction, an AB interaction, and so forth. There are also quadratic effects, AA and BB. AA is filter tabs squared. BB is sampling frequency squared. Since we had 3 levels of each of those factors, we could add quadratic terms to the model. And you can see everything except CD, which is the interaction amongst our 2 noise factors. All the other effects are statistically significant. Now, what I really need to point out here, and what's perhaps most interesting from the point of view of robust parameter design, are the interactions between the process variables and the noise variables. For example, you see here a quite large interaction between sampling frequency, that's factor B, and image bits. If there were no interaction between the process factors and the noise factors, it would imply that the effect of the noise was the same at every level of that process factor, which means that basically there were no particular robust conditions. If, however, the interactions, if a noise factor interacts with a controllable factor, it says that the effect of the noise is different at different levels of the controllable factor. So what we'd want to do is we'd want to try to find the level of the controllable factor such that the effect of the noise was as small as possible. Okay. And it's actually those interactions, BC, AC, BD, AD, the interactions between the noise factors and the controllable factors that are the key to being able to find the robust operating conditions. Okay. Now, the best way to see all this, incidentally, is to push the Tables and Graphs button in the analysis window here and ask for interaction plots. Interaction plots are quite important. They show you how the effect of one factor varies with the level of another. Now, the first thing you get, the initial interaction plot tries to show you every interaction. I usually find that a little bit difficult to interpret. So I'm going to push my right mouse button, go to Pane Options, and start by picking, let's pick the first two factors. These are the process factors. And pressing OK. Now, what we are plotting on the y-axis here will be the reception quality. And as you remember, the higher the better in terms of reception quality. The greater the better. You can see actually quite a strong interaction. If the two lines on an interaction plot are not parallel, and obviously these are not, it implies an interaction. And there is a fairly strong interaction in this case between our two controllable factors. You can see that overall high sampling frequency tends to be good. However, if you're at low filter tabs, sampling frequency doesn't have much of an impact. On the other hand, at high filter tabs, sampling frequency does make a big difference. Classic interaction here where the effect of one of my factors depends upon the level of another. Optimal point here, because remember this was a three-level design, so we get some quadratic effect here, appears to be sort of a middle level of filter tabs and a high sampling frequency. That certainly gives me the best mean reception quality. And if all I was doing was optimizing the mean, I'd say, pick filter tabs are, somewhere between 5 and 21, maybe it's around 12 or something like that, and as high a sampling frequency as you can get, and that would maximize reception quality. However, the goal here is not only to maximize the reception quality, but also to find a location in the controllable factors, a value of filter tabs and sampling frequency, where the noise doesn't have a big impact. And you can see that pretty nicely if you press the right mouse button, go to Pane Options, and plot, instead of both process variables, perhaps sampling frequency and image bits, BC, which is one of the very large interactions. What this will show you is that the reception quality is definitely impacted by image bits. But the impact is greater at certain sampling frequencies than it is at another. Now remember, image bits is a noise factor. And if you look at the reception quality at low sampling frequency for 256 bits, it's good, but for 512 bits, it's not good. On the other hand, at 13.5 sampling frequency, we get pretty good quality at both levels of image bits. In other words, at high sampling frequency, quality is not very sensitive to variation in image bits. Remember, image bits is something that's a noise factor that's normally not controllable. Well, that means that a high sampling frequency here is a location at which the quality is robust against variation in image bits. Okay. You can also try another one. I also did this with respect in the notes that you'll be getting with respect to filter tabs. Okay. And you can see that the more robust level of filter tabs is the low level of filter tabs. At a filter tab of 5, image bits has the least impact. Now you may remember that to get the optimal mean, the best value of the mean quality, we went for something like 12 filter tabs. On the other hand, you can see that you'll reduce the impact, reduce the variability due to image bits if you actually bring filter tabs all the way down to 5. So the location of optimal mean quality may not be the same as the optimal location with respect to the standard deviation of quality. Well, how do we get a single optimal condition? Well, the way Statgraphics has done this, let me go back to my PowerPoint slide for a moment, is we've used the same approach for optimizing a response, a robust parameter design, as we use when there are multiple responses. We define something called desirability. Now, if you've heard me talk before about multiple responses, you know that desirability is a metric that varies on a scale going from 0 to 1. 0 means not at all desirable, 1 means extremely desirable. And what it is, it's a measure of how desirable the values are of the responses at some combination of the experimental factors. And some of the plots that we'll do in a moment will show how desirability varies over the space of the controllable factors. Now, in this case, in a robust parameter design, we set up desirability so it's a combination of both the mean response and the standard deviation of the response. You define desirability for the mean, you define the desirability of the standard deviation. And actually the way desirability functions work, if you multiply the desirability of multiple responses together, the desirability of the mean with the desirability of the standard deviation, you get a single desirability metric that you can then optimize. The key to having this work in the response surface approach and Montgomery's approach is, as I hinted before, the interactions between the noise factors, the z's, and the x factors, the controllable factors. And in fact, if you read Montgomery's book, he'll give you a number of different equations for how one can determine, based upon the partial derivatives of the response with respect to those noise factors, what the standard error will be at any combination of the controllable factors. Here I've written down what's called the transmission of error formula that shows, based upon both the standard deviation of the experiment, and sigma squared here is your normal experimental error, but also sigma z, the standard deviation of the noise variables, what the overall standard deviation of the response would be. That's the formula that's actually used to calculate and plot the standard error, in this case of reception quality, at different combinations of the x variables. Okay. Now let me show you how that's actually done. It's quite easy to do. What we do, once we have fit our mathematical model, is we go back to the experimental design wizard. And we could just go ahead right now, if we wanted to take all the defaults and press step 9, optimize responses, and we'd do a simultaneous optimization of the mean and the standard deviation. I want to show you one other dialog box, however. If I push the right mouse button and go to Analysis Options, there are a number of options in the design wizard that have to do with robust parameter designs. First off, you need to tell it what your design region is. Over what region do you want to do your optimization? Now, usually we optimize over a cuboidal region. That is, over the region covered by the experiment, which in this case is basically a hypercube in 5 dimensions, bounded by the highs and lows. Well, hypercube actually only 2 dimensions. We have only 2 controllable factors. So it's actually just a square. I guess that's a very simple hypercube. Just a square bounded by high and low filter tabs, high and low sampling frequencies. And again, the optimization will be done as it was in the Taguchi approach, just over the controllable factors. The noise factors are considered to be uncontrollable in practice. We also, though, need to specify a couple options in order to do this combined optimization. The first thing that we specify is the range of the noise factors. It wants to know, looking at the high and the low of the noise factors, over what range of standard deviation of those factors did you vary. Now, it's common in robust parameter designs to basically take the average value of a noise factor and to take plus and minus 1 standard deviation on either side to specify the highs and the lows. Okay? Here you're telling it, basically, if you look at the high and the low of each of my noise factors, over how many sigma is that difference? And it's set by default to 2 sigma, telling the program that you have varied each of your noise factors over approximately plus or minus 1 sigma for a range of 2 sigma. Now, it turns out that's not critical with respect to finding out the optimal condition. It does, however, affect the plots of the standard errors, because what you're telling it implicitly is what sigma z is in this particular calculation, so it can plot the standard error. And often you might have an idea of how your noise factors varied and about what their standard deviation was, so you pick perhaps plus or minus 1 sigma for the range. You also specify, for combining the standard deviation to the mean, how important it is to minimize the standard deviation relative to optimizing the mean. You may remember, if you've seen the discussion of multiple response optimizations, that when you combine the desirability for multiple responses together, you can give one response more importance than another. By default, it's set to 1, which tells it the standard deviation is equally important to the mean. If the standard deviation was 3 times as important as the mean, you'd put in a 3. Then there's one more technical parameter, which also doesn't affect the optimization very much. It's the maximum for the standard deviation in the desirability function. Okay, this would take a little too long to talk about here, and the results are not very sensitive to this number. It just basically says what would be completely undesirable quality. What gets a desirability of 0? And what we're saying is anything 10 times the overall standard error would, anything more than that we don't even want to consider. Now again, it doesn't have much impact on the results. So I would normally take all the defaults. The only things, the first 2 fields are the critical ones. What range is covered by your noise factor in terms of their standard deviation, and what is the relative importance of the standard deviation to the mean. Once that's specified, you can then go ahead and press step 9, optimize response. And as usual, I usually start my optimization from all points to make sure I get to the global optimum. And it seems to have found an optimal condition. And if I go down here, it says, here it is, factor settings at the optimum. You should run filter tabs, it says, at about 9.84. Notice that's a little lower than we might have expected if we were just optimizing the mean. I said something like 12, I think, to optimize the mean. 5 to optimize the standard deviation, so something in the middle, 9.8, will optimize the combined mean and standard deviation. Sampling frequency, high as we expected, 13.5. That's the upper limit on sampling frequency. Up at the top, it will give you the estimated prediction. It predicts a reception quality of 35.35, gives you upper and lower 95% limits on that prediction. Also shows you what it estimates the standard deviation would be at the optimum, in this case standard deviation of reception quality at about 0.74. So it's found a location that both maximizes quality, the mean reception quality, and at the same time attempts to minimize the standard deviation. Now, of course, we need to plot this out. And the best plot here, if I go back to step 6, evaluate design, I can ask for a desirability plot. Now, what the desirability plot will do is it will plot desirability as a function of any two controllable factors. In this case, I'm plotting it as a function of filter tabs and sampling frequency. And actually, to make this more interesting, I'm going to contour the surface, color-coded according to height. Here's a plot of the desirability. That's the combination of mean and standard deviation at various locations throughout my experimental region. The red area gives the most desirable results. And you can see it's up there toward a high sampling frequency, although we could also get pretty good results if we backed off on the sampling frequency and lowered the filter tabs at the same time. Optimal location, I believe, is right about here toward the back. Right? It was at about 9.8 filter tabs. That was right back about here at high sampling frequency. There's also one last plot to look at. If I push evaluate design again, I can ask for overlaid contour plots. What this will do is it will actually plot for me contour plots for reception quality and for the standard deviation of quality. Now, reception quality is a quadratic model. You might remember we fit terms involving a squared and b squared. So what we see is actually an elliptical contours. There's an ellipse running through here, portions of other ellipses running down through here. Optimal condition for reception quality would be right about here, the center of that ellipse at the top. Unfortunately, that's outside the experimental region, whereas the optimization was only done over the experimental region. That square, incidentally, is the experimental region, so it couldn't get to the global optimum. It brought it basically back here to get to 13.5 to be within the experimental region. The red lines, on the other hand, are contour lines for the standard deviation, and they go down as you go up toward the upper left corner. So you can see, and it's actually moved, I believe, the optimum a little bit. If you were just optimizing the mean, you probably would have been here. To bring the standard deviation down a little bit, it did move a little bit off the optimal condition for the mean. So that is the optimal point, and you can see that's going to give me pretty high quality and also a pretty low standard deviation. Now, the interesting thing, again, I hope you will all read Montgomery's book. What we've done here with the combined approach is we've been able to uncouple the mean from the standard deviation. You see here basically one model for the mean and another model for the standard deviation. And those interaction plots we looked at earlier also give you a lot of insight about what factors have a big impact on the mean and what factors have a big impact on the standard deviation. My last PowerPoint slide gives you places to look for more information. The book I've mentioned several times, which is a really excellent book, not only on robust parameter designs, but on all sorts of experimental designs, is the book by Myers, Montgomery, and Anderson Cook. It's called Response Surface Methodology, Product and Process Optimization Using Designed Experiments. You can get the third edition now. It came out in 2009. And if you want all the details about how Statgraphics does its calculations, we did follow very closely the methodology outlined in that particular textbook. There are also 2 PDF files that talk about these 2 examples. They're installed and available from the Help menu once you're inside Statgraphics. If you select Help Procedure Documentation, the first is called DOE Wizard Inner and Outer Arrays. That will show you the Taguchi approach. And then DOE Wizard Robust Parameter Designs will show you the response surface approach. And of course, there are lots of resources also on our website. That ends the presentation. Let me now go back to my GoToWebinar window and see whether or not anyone's given me some questions. Okay, looks like we've got a couple questions. The first question, isn't a noise factor then the same thing as a controllable factor as long as the NF is always in the expected range, as long as the noise factor is always in the expected range? Well, the noise factors can be just deviations of the controllable factors, or they can be completely separate. For example, in the first example where we did the soldering example, the control factors were things like, what was it, temperature, conveyor speed, that sort of thing. The noise factors, well, one was the variation in temperature. That is actually just a change in one of the controllable factors. The second is variation in controller speed. Third, though, was type of assembly. I assume they solder different types of assemblies, so you can't basically hold that fixed. The important thing about the controllable factors is these are factors that typically we attempt at least to hold fixed. You know, we attempt, for example, to run at 280 degrees. The noise factors are things that during production tend to vary. And the first here was deviation from the attempted set temperature. So we might have attempted in general to hit 280 degrees. You know, 1 hour it might be 285, the next hour 275. So in that case, the noise factors are variations in the levels of the controllable factors. But in other cases, they're completely different. For example, type of assembly is not something I can even attempt to set. I do different assemblies, so that varies. Relative humidity, operators, and so forth. Okay. A second question I see here, yes, it's a little bit different from today's topic. Does Statgraphics serve as a good econometric software? Statgraphics is very useful whenever you collect data. A lot of financial data can obviously be analyzed statistically. We have whole groups of people out there who are using Statgraphics to forecast stock prices, to analyze exchange rates, to try to determine when it would be a good time to buy oil on the stock market. I know I do talk a lot about production examples, but there's an awful lot of good applications in financial analysis where you can use the same types of statistical models to do the analysis. And I know, for example, people use Statgraphics, use regression models to try to predict what housing prices will do, what rents you can obtain, and so forth. So if you've got the data, you've got response variables, and you've got predictive factors, as you often would in econometrics, Statgraphics can also do a good job on that type of data. Okay. So for those of you who aren't in manufacturing, I do apologize, I guess, for all the manufacturing examples, when there are lots and lots of other types of analysis that can be done. I'll tell you what, for the next webinar, which is going to be on the analysis of variance, I'll pull up some econometric data and do some good financial examples. Third question, how do we calculate the number of runs for a crossed array? 2 squared is 4. Okay, well, if you're doing the crossed array, and if you're using Taguchi's approach, then an L8 design will have 8 runs. An L9 design will have 9 runs, and L27 will have 27 runs, and so forth. So the number right after the L is the number of runs. Now, what you do, though, if you're doing any crossed array, and it could be a cross between a Box-Benkin design and a fractional factorial, doesn't really matter. Any designs can be used. You set up one design with a certain number of runs for the controllable factors, another design with a certain number of runs for the noise factors, and run every point in the noise design at every point in the controllable factors design, so the overall number of runs is the product of how many runs there is in the controllable design and how many runs you have in the noise design. So you figure out how many runs there are in the inner array, multiply by the number of runs in the outer array, and that's the number of total runs. Another question, how can we find good material related to econometrics applications of Statgraphics? I'll tell you what, I'll do some research on that one. And again, in the next webinar, when I'll talk about analysis of variance, I'll try to give you some good references for econometrics applications. Question 5, do these approaches lead to similar conclusions about values of controllable factors? Well, that's an interesting question. If you think about what's being done in these two different approaches, what happens at the crossed approach is that you take and you set up a design for your controllable factors. And at each point in the space, each run of the design for the controllable factors, you do multiple runs. You change the noise factors so that for every run in the inner design, you get directly a mean and a standard deviation. For example, we did an L8 with an L4. That meant that at every point in the L8 design, I did 4 runs where I varied the noise factors, so I could compute a mean and a standard deviation amongst those 4 runs. And then you directly model the mean and the standard deviation, or you model the signal-to-noise ratio and come up with an optimal set of conditions. In the second approach, you don't do multiple runs at necessarily a particular combination of the controllable factors. Rather, you infer what the standard deviation would be from the interaction between the noise factors and the experimental factors. You would think that both approaches could be used to get you to a good set of conditions. I'm sure they're not going to give you exactly the same set of conditions. But one would hope that most of the time either approach would take you to a good set of robust operating conditions. The thing that Montgomery likes, if you read his book about the combined approach, is that you get to basically analyze both the controllable factors and the noise factors together. So it's easy to visually see through those interaction approaches and so forth, the interaction plots, what factors have a big impact on the mean and what factors have a bigger impact on the noise. You get a little bit more understanding about what's happening by having a separate model for the mean and the standard deviation and being able to see what's happening for both of those parameters. A little bit easier to understand, at least for me, than looking necessarily just at a single number like the signal-to-noise ratio. Although one would hope they could both find a good set of robust operating conditions. Oh, now I see there's a question. Can you elaborate on the controversy regarding Taguchi signal-to-noise ratios? Not as well as Myers, Montgomery, and Anderson Cook do in their book. They've got a very nice discussion about the problem with the signal-to-noise ratios. I did hint at one of the problems. One of the biggest problems that it couples is that it couples together the mean and the standard deviation. Here's the slide that I had shown before with the signal-to-noise ratio that we were looking at, the one for smaller the better. What this is a combination of the mean squared and the standard deviation squared. Well, you can imagine that simply by minimizing that signal-to-noise ratio doesn't necessarily imply that you get the smallest mean or the smallest standard deviation, or necessarily that they should be weighted as they are here pretty much equally. You just get a single statistic that can be somewhat difficult to interpret. There are better approaches statistically in terms of optimization. They also criticize the fact that it's not really a signal-to-noise ratio. It's not really a ratio of any sort, nor is it signal-to-noise. It's almost signal plus noise rather than the signal-to-noise ratio. Also, as we saw, we come up with numbers like -39 or something like that on the signal-to-noise ratio, which doesn't necessarily have much intuition going for it when you need to interpret it. Again, if you could take a look at Myers and Montgomery and Anderson Cook's book, they do a relatively short but good discussion of some of the criticisms of Taguchi's ratios. They also, though, go on to say that Taguchi has been quite successful in optimizing many processes. Oh, another controversy that I should mention, since you did bring it up, is the fact that in many cases Taguchi ignores any interactions amongst the process factors, the controllable factors. In fact, a lot of the designs that he proposes, like the L8 design that we used, basically ignores the potential of any interactions between the controllable factors. Montgomery calls it the pick-the-winner sort of basis, where you look at a plot like this, a mean effects plot, and pick either high or low temperature, high or low flux density, and so forth. If the factors in fact interact, then you don't necessarily get the best results overall if you just pick separately the best results for each one of the factors. So the fact that a lot of Taguchi's designs ignore interactions may lead you to a point that's not optimal, or since the interactions are confounded with the main effects, may lead you to erroneous conclusions. Although they do say in this same textbook that there are lots of instances where Taguchi's approach has been quite successful. Often, certainly widely used by the automotive industry and very successfully used back in the 1980s. It may be in those kinds of situations, interactions are not very large, so that one can get a pretty good result by simply picking the optimal levels of each factor separately. Okay, that appears to be the last question. What we will do is what we have done in the past on these webinars. We will publish and put on our website a recording of the webinar. I'll put up the PowerPoint slides, and I'll give you the sample data files that if you want to analyze them yourselves.